Emerging non-volatile memories will drive the adoption of new computer architectures, which will use non-volatile memories for near memory and for shared far memory. Emerging non-volatile memory technologies, including 3D XPoint, MRAM, and resistive RAM, are now available in the data center and will become common in AI-based Internet of Things devices. Over the long term, these new memories will play a big role in the data center, at the edge, and at IoT endpoints. I'm Tom Coughlin.
And I'm Jim Handy.
We're the co-authors of a new report that examines emerging memory technologies and forecasts the markets for these technologies and the capital spending that they will require. In this presentation, we will explore how new emerging memory technologies will drive changes in computer architectures and how these changes will subsequently drive new support requirements that will have a lasting impact on how computing systems are designed in the future. I'll let Jim give you the presentation outline for us to get started.
Where will we take you on this brief trip? First, we briefly touch on the status of emerging memory technologies. We could go deeper because we wrote a thorough report on that, but we'll tell you about that later. Next, we'll show you what happens when you start to use emerging memories in standard computing systems. A lot has to change if you want them to use them to their best advantage. This naturally brings us to a discussion of changes to computer architecture, so that will be our next section. Finally, we'll talk about where we see computing headed in the future. After that, we'll take as many live questions as time permits. And now back to Tom.
Thanks, Jim. So let's talk about these emerging memories, especially the ones that are now available in volume. There are many emerging memory types in production today. All share the same attributes, which I will detail in an upcoming slide. Their most important advantage is that they can all scale to smaller bit sizes than can today's established technologies, allowing continued cost reductions. New memories are necessary for Moore's law type scaling to continue. These technologies include ferroelectric random access memory, magnetic RAM, resistive RAM, and phase change memory, such as Intel's 3D XPoint, which they sell as Optane memory. This chart comes from a new report that Jim and I published called Emerging Memories Take Off. We will tell you more about that soon. We put together a forecast of all memory types and found that the total emerging memory market, shown by the 3D XPoint and MRAM lines here, could exceed $44 billion by 2031. This chart shows how petabyte shipment growth could drive that number. This figure compares the current and projected petabyte shipments for the next 10 years for various emerging non-volatile memory technologies, again, MRAM and 3D XPoint, versus DRAM and NAND. We don't see DRAM and NAND going away anytime soon, but we do see other memories making serious inroads as computing architectures change to take advantage of them. Assumptions behind this chart are that 3D XPoint penetrates 50% of servers by 2031. Embedded MRAM will replace most of the embedded NOR and SRAM in system-on-chips, and MRAM will have a strong appeal for AI applications. We don't know for certain what the future will bring, but this scenario is a definite possibility. All emerging memory types share a number of attributes. They all have a bit cell that promises to scale smaller than current technologies to support small, inexpensive arrays. Most of them can support 3D stacking to reach even lower costs. They also promise to be easier to use than flash memory by supporting write-in-place with no need for a block erase, and they have more symmetrical read and write speeds. Finally, they are all non-volatile or persistent. Data doesn't disappear when power is lost. They can all be used as persistent memory. New memories are necessary for this Moore's law type scaling to continue. Their biggest problem is a chicken and egg issue. They need to compete on price against established technologies, but their price can't profitably be driven down until their unit volume approaches that of DRAM and NAND, flash. They need to overcome this economy of scale. All of this is thoroughly explained in our newly released report on emerging memories. The report that this data comes from is available to purchase online. It describes the entire emerging memory ecosystem, including the technologies, phase change memory, resistive RAM, magnetic RAM, and ferroelectric RAM, the companies, the markets, support requirements, including the capital equipment projections required to support this growth. The forecast examines emerging memory consumption, both as embedded memories in system on chips as well as discrete chips. It's 230 pages long with 36 tables and 155 figures. Visit the URLs at the bottom of this slide to learn more. With that, I will turn this back over to Jim.
Thanks, Tom. Emerging memories bring new benefits to computing, but they also need a lot of new kinds of support. Let's examine that. How do computing systems work today? Every system has three elements: a processor, a memory, and I/O. In this case, we'll only show the storage part of the I/O. The processor has three parts: a CPU, registers, the fastest form of memory, and a cache. Next comes memory, the DRAM chips that live outside the processor. Finally, storage, where the data and programs permanently reside. Storage has always been persistent. With 3D XPoint Optane memory, the memory also can become persistent. Since NOR flash doesn't scale past 28 nanometers, and since SRAM scales poorly as processes shrink at 20 nanometers and beyond, the cache memory and eventually the registers on the processor chip are likely to migrate from SRAM cells to an emerging memory cell. Today, MRAM looks like the leading candidate for this distinction. Let's focus on memory, since that's where most of today's activity is centered. The two biggest issues are the interface, DDR, and the required software support. DDR4 is today's prevalent DRAM interface. It's running into issues. DDR has been configured to support one kind of memory at a single speed. Since 3D XPoint is slower than DRAM, and since its read and write speeds are different from each other, Intel had to define a new bus that would handle both memory types. Although it would be reasonable for the memory controller to reside within the memory, allowing the CPU to do CPU chores while the memory did memory chores, that's not the way it's done today. Today, the memory controller is a part of the processor. This makes it inordinately costly. It also prevents the processor from interacting with a variety of memory types, and persistence has posed some vexing problems to processor designers. Meanwhile, new software and expanding datasets are driving the need for systems to expand memory and to communicate with it at ever-increasing speeds. These two requirements are in conflict with each other because of capacitance issues. As bus clock speeds increase, systems must reduce the number of DIMMs that can be attached to the memory channel. The memory can either be large or fast, but it can't be both. DDR was a really good choice in the early part of this century, but today it seems it needs to be replaced by something else. Meanwhile, current software has enormous difficulty taking advantage of the persistence that new memories provide. This software was written to operate in a space where storage was persistent and memory was not. To deal with persistent memory, these programs must be reconfigured. It will take a lot of time before these programs can be hardened and trusted by customers. These customers will realize an immediate benefit once they adopt PM, but they don't want to take chances right now. There are other considerations when PM is used. What happens to the cache memory? If the software performs a write, and if that write is assumed to be persistent, then there must be a copy in the persistent memory, and not just in the cache. Intel's architects understood this, and a few years ago they put together instructions in the Intel architecture, or IA, to flush the cache upon command to the persistent memory. Finally, security is a concern. If data is made persistent in the memory, then steps must be taken to assure that nobody gains access to the data within that memory after a computer is decommissioned. Tom will walk you through some of this.
Computer architecture must change to handle the issues that Jim just discussed. Let's have a look at how these problems are being addressed. One new approach is the use of far memory. Until recently, two systems would read and write to each other's memories slowly through the I/O channel. With the growing adoption of GPU as AI accelerators, this approach severely limited performance. A new idea was adopted, What if all memories could appear as part of the server's memory? A server has its own DDR memory. A GPU has a memory of its own, too. It's often an HBM or high bandwidth memory. A number of interfaces, including CXL, have been developed to allow the server to access the GPU's memory as if it were a slower part of the server's overall memory complement. Likewise, the GPU can read and write to the server's memory at a slower speed than it can its own. While it's slower, it's a whole lot faster than using an I/O channel. It also doesn't matter if the two systems are using different memory types, in this case DDR and HBM. CXL hides these differences. But there's another great use for these technologies. You don't need to have a GPU to use them. You can simply have a pool of memory, and this pool can be shared among a number of servers. The memory pool doesn't have to be DDR or even DRAM either, but it can include 3D crosspoint memory or any of the other technologies that we discussed earlier. The CXL interface hides the differences between these technologies from the server. You could do something similar to that for near memory, if you choose the right interface. Here we have a Power 10 processor connected to 8 OMI differential DIMMs, one for each channel on that side of the processor. OMI is an alternative to DDR that is similar to CXL in that it can hide the differences between different memory types. But OMI works for near memory, while CXL is the solution for far memory problems. What will we attach to the Power processor's OMI channels? Well, DDR4 is today's most obvious choice, but there's no reason that we couldn't add DDR5 later on, once DDR5 prices drop below those of DDR4. Through the OMI channel, they will look the same. In fact, you can make a DIMM with, say, LPDDR, and have all three of these technologies running in your system at the same time. But there are other possibilities too. Just as you can run several different DRAM types in the same system, you could add another memory type, say 3D crosspoint, to the system. But it doesn't stop there. A single system could have different memory types on each and every OMI channel, without the processor needing to worry about the differences between them.
But all of this takes support. SNIA has been working for the past 8 years on the NVM programming model to support persistent memory. This well-conceived approach provides a consistent, unified means for applications programs to operate in an environment that includes both persistent memory and more conventional memory and storage. Old applications can perform in this environment without change, and new applications can be developed to tap into all that persistent memory has to offer. Intel, meanwhile, has been developing lower-level support for persistent memory in its systems. It has developed 2 different user modes for persistent memory, the first of which takes advantage of the persistence of 3D crosspoint memory, and the other which treats it as a big DRAM, completely ignoring its persistence. And we already told you about the new instructions to the Intel architecture instruction set to assure that dirty cache lines can be saved to persistent memory in the event of a power failure. The problem is mind-blowingly complex. So where do we go from here? Persistence will enter computing architectures step by step. SNIA has already taken the first step by introducing the NVM programming model and is helping to work out the new security issues that develop with the adoption of persistent memory. After that, CXL and other interfaces were developed to support mixed memory types in far memory, and OMI brings a similar capability to near memory. Both of these interfaces help to hide the speed differences between a variety of memory types and to offload the DRAM management and I/O burden from the processor chip. OMI helps to move beyond the DDR's tug-of-war that pits bandwidth against memory size. As persistence moves into the processor itself, there will be a need for policies for persistent cache, and then, after that, policies for persistent registers. And all the while, security will need to be constantly reconsidered, spanning the whole shebang. But that's not enough for now. Your heads may already be spinning from all of these new considerations. Let's open the floor to questions and see what happens.